Greetings, the Astro 30 here yet again with another short circuits assembly kit. In today's video we're going to be looking at the Hee-Haw Siren with flashing LED. It's basically like, you know, a police car siren. Anyway, it says use this project make a sound like, that's bad English. Use this project make a sound like the siren of an ambulance. Features alternating flashing red and green LEDs. Countless applications such as grabbing someone's attention. And it's KJ8204, Short Circuits Volume 2, Project 3. Kit includes PCB, speaker and electronic components. Kit requires 9-volt battery and instructions. KJ8205 or Project Book BJ8504. Optional UB5 Jiffy Box. So I suppose the first thing we should do is actually have a look in the project book at Project 3. Just to have a look at the schematic and see how it works. Okay, so I'm redoing this bit because my original explanation sucked. However, on page 37 of the short circuits book here, we've got the schematic for the siren, and over here it's pretty standard. We've got a 9-volt battery plus a wrong wave protection diode, which is also a half wave rectifier, and it goes through this 1000 microfarad filtering capacitor. So technically speaking, you could actually power this off of a 7.5 volt AC adapter or something, and then rectify it with this half wave and then filter it. It might produce a bit of mains hum or not, I'm not too sure, but that's not what we're going to do. Now, the heart of the circuit is this 555 timer. They're very common, they've been around since the 70s, if not longer, and they're basically an oscillator, in a sense. And in this case, we're using it as an oscillator. Now, the basic frequency that it oscillates at is being set with this feedback resistor of 100k between the output pin 3 and these two sense pins, pins 2 and pin 6, and also controlled by this 10 nanofarad capacitor. And that gives us our basic oscillation or one-tone sound. The speaker is connected from pin 3 to the positive rail via these two 150 ohm resistors. That would give you roughly half that value, which is 75 ohm, somewhere around about there. And that's basically using this configuration like this to switch between 0, or the negative 9 volt, and the plus voltage rail here. These resistors are just used to reduce the current flowing through the speaker so that it keeps this IC happy, because if we didn't have these here, this IC would not last long because they're not good at sinking large amounts of current. Now, the interesting part about this circuit is this multi-vibrator circuit over here, and that just basically means basic oscillator. It's a 2-transistor jobby, and this is not usually how you draw it, but this is just how it's drawn for clarity, but you often see it drawn in crisscross pattern like that. I'll do a separate video on multi-vibrator circuits later, but basically the operation is simple. We've got two base bias resistors here, 100k, and two 22 microfarad capacitors here. Now, the speed or frequency of the oscillation that these switch back and forth is controlled by these two resistors and these two capacitors. And these LEDs and resistors just complete a current path back to the positive rail for the transistors to operate. How we get the IC here to make the Hee-Haw sound effect, so we got one base frequency of He. How do we make it switch to the lower Haw frequency? And that's H-A-W, not the other one. Well, notice this 10k resistor here. It's connected off the collector of transistor Q2 here. So when this green side LED transistor is conducting, it's going through this 10k resistor which is going into the pin 5 of the 555 IC, which is its control pin, and basically we're varying the voltage on that control pin. So if we vary the voltage here, we can actually change the pitch of the oscillation. Remember, the base oscillation is controlled by these two components, the resistor and the capacitor, across pins 2 and 6 and 3 respectively, and the actual up-down sound of the oscillator changing frequency is controlled by pin 5. But that's how that works. It's using these two transistors in the multivibrator to control the tone of the output of this 555. And that also means that these lights will flash in sequence with the changing sound, so that they're not going out of sync. Now, the actual speed of oscillation, like the change in the sound, like the Hee and the Haw sound, is determined by these two capacitors and these two resistors. If you increase either of these values, it would lengthen the delay time between the switching. If you reduce them, it'll shorten the delay time between the switching. Now, in this configuration here, it's roughly at 0.5 Hertz. So that's half a second, thereabouts. So it's Hee for half a second, Haw for half a second, and vice versa. So it's a fairly slow oscillating circuit. But they do say in the text of this book here to experiment with those values. If you want a lower sounding siren, you would change this 10 nanofarad to a higher value, say a 22 nanofarad. The higher the capacitor you use here, the lower the frequency. Conversely, the lower the capacitance here, say 4.7 nanofarad, the higher pitched or more shrill sounding the oscillator will sound. So as they say in the text, those are the two modifications you can play around with. If you want a higher pitch sound or a lower pitch sound, you modify this capacitor. If you want a faster running circuit, so it's going hee-haw, 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 you would modify these values of resistors and capacitors. But if you want to keep it an even Hee between Haw, Hee-haw, Hee-haw, all values must be changed to the same values. So if you lower these to say 56k, they both have to be 56k, and these two, 10 microfarad for instance, they have to both be 10 microfarad to make it balanced switching. Otherwise, if you have a higher value here and a lower value over here, it'll be like that. It'll be on quick, off long, on quick, off long, basically speaking. So if you keep the values balanced, is the word I'm looking for, you'll get a balanced switching frequency. So changing these to 10 microfarads will change it to roughly 250 milliseconds of switching between the two. So one will be on for 250 milliseconds and one will be off for 250 milliseconds, and vice versa. So that would give you a hee-haw, hee-haw, hee-haw basically sound. Now I'm starting to sound like a police car. Anyway, I think that's enough talking about the circuit. I've gone on way too long about discussing something as simple as this. But as I've said in previous videos, it's not learning anything if you don't actually investigate how a circuit works. Just building it and saying, yeah, it works is great, but it doesn't actually teach you anything. It's just that you're copying somebody else's work, basically. It's the same as if you're at high school and you're copying the person sitting next to you's math exam. You don't learn anything from it. Yeah, sure, you pass, but you don't learn anything, and you're basically cheating. In electronics like this, it's not cheating just to build something without looking at the circuit. Yeah, sure, but it does help to have a basic knowledge of how the circuit operates, so when it doesn't operate the way it's supposed to, you can have a better chance of fault finding why it doesn't. So let's open the packaging here. This kit was only about $12. It's not that expensive. Again, we have the advertising material for the book. Not very exciting. And their standard AS3000 54mm speaker. A bag of parts. It's a very simple kit to build, by the way. Both transistors are the same. their PN100, which is MPN. There's a 555 timer there, and a bunch of PCB pins at the top. They also give you the battery clip, so it requires a 9-volt battery. I might actually power this off the 9-volt, well, off the variable bench supply. And of course our PCB, which is fairly simple to assemble. I would start with all the resistors first and the PCB pins, and then move up to the capacitors and the IC. I might install an IC socket because, as I said in the last video, I've got stacks of them, so I might as well use them. So we'll put this in something to hold it and we'll start assembling it. Alright, now the problem with doing videos like this is the tripod's always in the way. I wish I had some sort of ceiling mounted device to do this with, but I don't. So I've got the circuit board mounted in this stupid holding tool thing. So I'm going to start with the PCB pins. There's only 4 of them, and the reason why I'm starting with the PCB pins is because, well, considering it's up in the air, it doesn't really matter about the profile of components because the tool holds it for me where I want, so it doesn't really particularly matter the order in which I do things. If you're doing it just sitting on the desk, like I have sometimes done, then yeah, you'd probably want to do the lower profile components first before said PCB pins. So I'm just going to do this at a right angle. Next I'm going to install this IC socket, and so I'll just get one pin started to hold it straight. And then I'll solder the opposite pin. Right, and now go down the line and solder the rest of the pins. I did actually have another project planned for this weekend, well today anyway, but in the end I couldn't be bothered because I really can't be bothered thinking. So that's the IC socket installed. You don't need to put one in, but I'm just putting one in for the sake of putting one in. So we'll do that other project later, but for now I'm going to focus on this. I'm going to do the resistors next. That's a 100k. Well, it can't be because there's 2 of them. See, some of these are hard to read. That's a red, so that'll be a 10k, and there's only one of them. So we'll go with 10k. It's brown, black, red, but I mistook that for an orange. This is the reason why with these 5-band resistors you would often measure them with a multimeter just to make sure. But because there's only 4, 8, 10, 12 resistors, and most of them are doubles, it really doesn't matter. When I was a kid, I had this science fair 160, I think it was 160, 161, something like that, in one project kit, and I used to play a lot. They had this hearing aid amplifier, which was a 3-stage transistor amplifier, and they also had quite a fair few oscillators and, you know, sirens, and I used to play with them a lot, as well as the radio circuits. And I used to modify them. I took the hearing aid amplifier, which was Project 3 in the book, and I actually reversed the input and output around because I used basically a 54mm speaker like this as the microphone going through a 8 ohm to 1k transformer, and they also had an input transformer which was a 3k to 3k, I think it was, something like that, and I reversed it round so the speaker was outputting, and then I connected another audio source to the input and turned it into a little amplifier, which it already was, but you know what I mean. I reversed its actual application, or changed its actual application. And also I used to modify with the sirens, and I made this siren which was supposed to oscillate at like a ooh, ooh, but I made it go etc. And it took about 5 minutes to get to its peak frequency and then discharge. So I'm up to the last 2 resistors. which are 150 ohm. And then we can move on to, well, there's supposed to be a diode, but I think it's in a different bag. Yes, it is. You know, I could have just breadboarded this rather than buy the kit, but yeah, breadboarding takes effort and time, whereas you can just solder this up without having to worry about where this wire has to connect and that wire has to connect. I will breadboard some of the circuits though. Just for, well, yeah, I suppose I could have breadboarded it, but I don't think I actually have any 555 timer ICs. That's kind of a shame. I should have bought some. They are a pretty commonly used IC in a lot of things, but I just don't have any. You can just bend the leads over at right angles with your fingers, but I'm using the pliers to make it a little bit more neater. And always observe polarity too of diodes and capacitors. So I'll just put the transistors in now because they were convenient. Wish my nose would stop running. It's always annoying when I go to film a video, I have a coughing fit before I start and then I can't stop sniffing. Okay, so might as well install the LEDs now. They're just standard 5mm LEDs. The shortest lead is the cathode. They also have a little flat on one side to denote where the cathode is. So we've got a green one which goes over here. Don't know whether to mount them flat with the board or not. Well, I suppose I shouldn't, because if you want to put it into a case that's, you know, so you want it up fairly high, I suppose, but there's no real description of how high to mount them. So what I'll do is I'll mount them as long as possible without being too long. And just guess roughly where to mount them. I'll get them started and then I'll straighten them. They look about the same height. I'm leaving myself a little bit more extra lead on there in case I want to, you know, shorten it. But I don't have a case for it, so there's no point worrying about it too much at this stage. I mean, you could always unsolder them and just, you know, replace the LEDs with new ones. It's not going to be that much of a bigger deal. Okay, so at this stage we can now put the capacitors in. We've got a 10 nanofarad capacitor here, which is just a standard polyester green cap, which is a 103. So that just sits in there like that. And that gets soldered in. And then all that's left is electrolytics. I'm going to start with this 1000 mica. So I'm just going to cut the band tag off. It's easier than trying to pull it out of the band tag. And put it in the correct way round. This is not a low ESR, it's just a pretty coloured capacitor. So that one goes in there. And then we have two 22 microfarad 50 volt caps. Again, just cut them off the band tag, band strip, and put them in the correct polarity. And just bend the leads over so they don't fall back out. Solder them in. Left that one until last because I bent it over a bit too far. There we go. And then cut off our excess lead. Don't know where that went, on the floor somewhere. And there we go, the circuit board is now complete. Didn't take too long. Well, I average about 25 minutes there, so that was including me talking. So I suppose I might mount some standoffs on this, and then I'll prepare the speaker lead that they've given us to connect the speaker with. It might be a good idea to insert the 555 timer whilst we're here. Make sure it is a 555 timer. Yes, it's an NE 555P. So that will go in there like that, and now that's the circuit board complete. So this tool can now go away. So just tighten these screws. This is not to assist in mounting it or anything, this is to stop it scratching around on the desk. And then I'll move on to doing the speaker wire. So that's that done. So I might as well use the wire that they've given us. The easiest way to do these is to take a knife blade, preferably put my eyes on so I can see what I'm doing, and I'm just going to push, not like that, and just pull the wire over the blade and not actually trying to slice the wire with the blade. So I just put it in the wire, pull the wire, and then that should separate it. So now all I need to do now is just strip it back on both ends. Stripping wires with a pair of side cutters does actually take practice and experience. I make it look easy because, well, I've done it for so many years. It's just knowing the thickness of your wire, how much pressure to put on your side cutter blades without actually ripping strands of the copper wire out of the wire itself. There's also another topic, I suppose, here, that you're not really supposed to twist the ends of the strands together, that I always have. But the reason behind that is because if you look at it carefully, you'll see that they're already twisted together, but it's only minutely twisted together. And you'll find when you go to tin the wire that it doesn't quite tin the strands together properly. So that's why I always give it a bit of a twist. So just trim off ends a bit. Okay, now I need the speaker. Oh, God, those speakers smell when you solder to them. Now there's a black line on this wire here, which I will use for the negative. And I'm going to try and pass the end of the wire through the eyelet, like so, which is the proper way to do it. That's why there's a hole there. So like that. And just lose the wire altogether, that'd be right. I was trying to be smart, but it didn't work. Sort of like that. That was what I was going for. Okay, so that's the speaker wire soldered onto the speaker. So I need to go to our speaker connection here, tin the PCB pins so that the wire will take to them. Take a striped wire and put it to the negative connection, which is basically the IC's output pin 3 anyway. It doesn't go to the negative rail or anything. But the IC itself is switching between the negative rail and positive rail. So that's the speaker connected. The circuit's now basically essentially, is now essentially ready for testing. So all I need to do is hook up a 9-volt power supply to it and see if this thing flashes its LEDs and makes a noise. Okay, I've got the circuit hooked up to the power supply, set at 9.2 volt roughly. So I'll turn it on and see what it does. Well, yeah, okay, that's annoying. That's basically what it does. It's not very fast, is it? You could modify the capacitor values here to make it, to make it oscillate a bit differently, like a little bit faster. But yeah, as exciting as that was, that's all it does. Nothing else. So yeah, that's really exciting. However, what I might do is I might hook the oscilloscope up to the output here and actually see how that IC is switching. Normally you would probably put a transistor buffer between the IC output and a speaker like this rather than connecting the speaker directly to the 555 timer, but however, these small speakers, these 555 timers are pretty resilient. Okay, I've got the oscilloscope hooked up. I'm at 2 volt. I might put that back to, 2 volts should do. Let's turn it on, see what the output looks like. Okay, as you can see, it's a very nasty looking square wave, and we're oscillating between 660 Hertz and 560 Hertz thereabouts. So those are the frequencies that it's oscillating at. But it was just a good visual representation of what the actual IC was doing. So anyway, that was a interesting little circuit to build. It's quite easy to build, and we've seen what the output does on an oscilloscope. For a little kit, it's not expensive, but it's at the same time not all that interesting either. But if you assemble it correctly and take the time to assemble it, you'll end up with something like this within about half an hour that just makes a noise as soon as you turn it on. Normally you'd wire the battery clip that's supplied across these terminals via a switch so you can turn it on and off. But I haven't done that. So I'm going to put this one away and move on to the next thing, which I don't know what that is. Don't know whether I'm planning on doing anything else today or not. But I'm going to say that this is the end of this video here, and I want to say to everybody thank you for watching. And as always, if you enjoyed this video, please remember to rate, comment and subscribe below. And you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying, Hee-Haw! Yeah, that's much better. I just vacuumed the floor of the lab. Now it's nice and clean, ready for the next time. By the way, I have a penis. I have a big penis. I've named him Bixby. Why? I don't know. Anyway, see you later.